Okay, so let's next talk about doubling constant. So the way to think about doubling constant is that it's a parameter that captures a dimension, which is related, of course, to the Euclidean dimensions. So let's first, we're going to be slightly in more abstract setting. So we have a metric space. To remind you, a metric space means we have a set of elements x, and we have a distance function, the metric, and the metric has to comply with the triangle inequality. And we can define, once we have a metric, we can naturally define a ball PR, P is of course, in the set X. This is all the points in the ground set X in capital X, such that the distance between X and P, let's say smaller equal than R, right? This is the closed ball. Okay, so what is the doubling constant? Doubling constant tries to capture the complexity of the metric space. So the doubling constant, let's call it C, of is minimum numbers of balls of radius R are needed to cover a ball of radius 2R. So maybe let's start with the most idiotic example, right? So the most idiotic example would be, of course, the real line, right? So we have an interval here. We have P, we have 2R and 2R. So a ball of radius 2R is just an interval of length 4R. And clearly we can cover it with two intervals, each is a ball of radius R, which, right, this is R, and R. So the doubling constant of the line is 2. Okay, not very interesting. Let's see, what about the plane, right? So let me draw a ball of radius 2. Okay, right, we can put a point here that would cover this. We can put here 4 balls here. That's doing pretty decent job, right? But it's not quite done, so we also will take a ball in the middle. Okay, that's good, but there are still parts that are not covered. We already spent 5 balls. And then I can take those 4 centers, right? And this is not bad, right? Don't misunderstand me. This is a pretty neat construction, and if you count it, it's 9. Okay, so the doubling constant C2 is at most 9. But the question, of course, is what is the right constant? And that's kind of an interesting question, so let me show you a very nice figure demonstrating. Okay, so here is the example. The disk here is the of radius 2, it's the blue disk, and we take the disk of radius 1 that is concentric with it, and we define the natural hexagon, and then we tile the plane with hexagon, right? And clearly, if we take the center hexagon and the 6th hexagon adjacent to it, it covers the disk of radius 2. And each hexagon is, of course, its center naturally define a disk of radius 1 that cover it. So in this case, we get C2 is equal to 7. Right? And it's not hard to verify that you cannot do better. Here 2 is just to say that we are in Euclidean 2-dimensional space. Now, what about d dimensions, right, in RD? So there things are a bit more tedious, but let's try to do it. And the trick is going to be that as long as I can find, I just put an arbiter. I'm going to take a ball of radius 2. This is in d dimensions. So think about d as 3 as 4. And what I'm going to do, I'm going to start, if I find a point that is not covered, well, nothing is covered in this ball currently, so I take an arbitrary point and I draw around it a ball of radius 2. That's what it covers. Now, as long as there is a point that is not covered, right, I pick this point and I cover it, right? And I repeat this process, right? So I repeat this process. Okay, and I think maybe, here it's done. Okay, the question is, so what we're going to look at to bound the number of balls we need to use, let me just look on the centers that I picked. I picked some centers. I picked the first one, the second one, the third one. By the way, this way of covering is sometimes called ice cream scooping. Let's not get exactly what I mean by that. We might come later to it. But the important thing to observe is that the distance between any two centers we picked is at least 1. Why? Because we picked one of those points first. Let's say this is P and this is Q. If I picked P first, then all the points in distance 1 from P are covered. So if we picked Q and it's not covered, it means that it must be a distance at least once, right? That in particular means that if you think about the points as centers of balls of radius half, those balls are disjoint, right? At least interior disjoint, right? So, except that the center might be on the boundary, so the balls might get outside a bit out. So to overcome this, let's, instead of looking of the ball of radius 2, let me look on ball of radius 2.5. Okay, so this is a ball of radius 2.5, and I have a bunch of balls of radius half, and they're all interior disjoint. Okay, now we can use the formula for the volume of the ball. Now, the volume of the ball in the dimension is some constant b of beta of d times r to the d. What exactly is beta to the d? That's a standard exercise in calculus, or you can just search the web. It's well known. They're closed form formulas. They're not pretty, but they exist, or at least they're slightly not pretty. But beta d, for a fixed d, beta d is a constant, right? In particular, if I look on a ball of radius 2.5r, I get 2.5r to the d. So this is the radius of the big enlarged ball of radius 2.5r. On the other hand, we're covering it by those tiny balls, salami slices, if you want to think about this as a d-dimensional pizza, or pepperoni, I guess, sorry, not salami. So each pepperoni piece has volume, beta d, r over 2 to the d, right? And now, so I claim the number of points is at most this fraction. Why is it correct? Well, I take the volume of the big ball, and every small ball, all the small balls, all the pepperoni pieces are disjoint. So the number of pepperoni pieces can be at most the volume of the large ball divided by the volume of the small balls. So this is this, and this is 5 to the d. So we get immediately that C of d, the doubling constant, is at most 5d, 5 to the power d. Okay? And you can do a lot of other examples. Maybe for abstract cases, think about, for example, a star. So a star is just a graph where all the edges, let's say, have length 1. There is one vertex in the middle, and they're all connected to the leaves, right? So, and it's not hard to verify. Okay, so now the edges of the length here are all 2, right? Because I want the ball of radius 2. But if I want to cover all the vertices, if I want to cover this graph by balls of radius 1, here, of course, ball of a certain radius is just you have a certain vertex and you take all the vertices a certain distance from it. But unfortunately here, ball of radius 1 cover only their own vertex. So you would need n vertices or n balls, which means that this doubling constant in this case is unbounded. It can be n, and n can be arbitrarily large. So doubling constant is arbitrarily large. And notice that this covers, for example, planar graphs, right? Because it's a planar. One can easily draw this graph in the plane. So this is true even for planar graphs. And one can do other examples, but maybe the most natural example is a manifold that you have points in d dimensions, but your points lie on some manifold. The manifold is only 2-dimensional. And if the manifold is not too crazy, you expect it to behave like two-dimensional entity, not like a d-dimensional entity. And there the doubling constant would probably be closer to the doubling constant of the manifold and not the ambient dimension d. Okay, so we will revisit this doubling constant and doubling dimension later. Maybe let me formally define the notion of a doubling dimension. So doubling dimension is just usually it's the d-dim of the metric space. This will be just the log of the doubling constant of the metric space, which we defined above, right? Okay, so the reason to think about this doubling dimension, doubling constant is because it abstracts away the notion of Euclidean dimension, and it turns out that algorithmically it's a very nice abstraction that really captures our intuition of what the dimension is, because, for example, it's easy to argue that if you look on RD, right, we already argued that the doubling constant is 5 to the, at most 5 to the d, and as such the doubling dimension of RD is O of d, is log of 5 to the d, which is O of d, right? So doubling dimension is indeed a natural extension of the notion of dimension. Okay? And this notion of covering something by balls is also a very important primitive operation that we will come back to it later.